So this is Dr. Shankaraiah from Department of Physics. So I am discussing about Module 1 crystal structure. So in today's presentation, I will discuss about structure and packing fraction of crystals. So in this structure and packing fraction of crystals, we will discuss basically cubic crystal. So crystal system, and we know that there are three different types of lattices in cubic crystal system. That is simple cubic, body centered cubic, and face centered cubic. So we will discuss about the structure and packing fraction of these three different types of cubic crystals, which is simple cubic, body centered cubic, and face centered cubic. So before going into details, we need to know about something about symmetries. What do you mean by symmetries in crystals, and why do we have only 14 Bravais lattices or why do we have only 7 crystals using these 14 Bravais lattices? So to understand that, we need to know what is the symmetry in crystals. So some similarities of atomic arrangements may occur in crystals as a result of periodic arrangements. Because of the periodic arrangement of atoms in crystals, we will find that there are some similarities of atomic arrangement. We know that because of the periodic arrangement of atom, at any point in a crystal, you are sitting at any point in a crystal, the neighborhood looks same as at any other point in the crystal, right? So because of these periodic arrangement of atoms, we will find that the atomic arrangements are same in different times in places. So this is called symmetry of atomic arrangement. Okay, so suppose I have one kind of atomic arrangement right now, right? So take any crystal, for example NaCl crystal. So NaCl, I have one atomic arrangement. This is my atomic arrangement. After some time, I have another. I am looking at the atomic arrangement again, and I find that the atomic arrangement is same even up at later times, right? NaCl. It may be different, it could be different, but I find the atomic arrangements are same at different times. Okay, so the similarities of the atomic arrangement is called, there is symmetry in the atomic arrangement, right? So this is called symmetry of atomic arrangement. Indeed, the crystal can be characterized by the symmetry it possesses. So you can explain, we can understand the crystal by looking at symmetry. Okay, by looking at symmetry present in the crystal, we can understand its characteristics, what kind of characteristics it can have, right? So yeah, so that is called symmetry of atomic arrangement. So crystals possess different external symmetries which are described by certain mental operations, right? So what are these mental operations? A symmetry operation is one that takes the crystal into a configuration identical to the initial configuration, right? So what do you mean by crystal possess different external symmetries. Different symmetries crystal possess, but how do we get these symmetries, which are described by these mental operations? By looking at different types of operations, we can understand these symmetries of the crystals, right? So what do you mean by this symmetric operation? Symmetric operation is one that takes the crystal into a configuration identical to an initial configuration, right? At t is equal 0, I have a configuration of the crystal. I am describing the crystal configuration by a lattice, space lattice, right? So this is the configuration of the crystal at time t is equal 0, and at time is equal to some t prime. It can be 3 seconds or 4 seconds or 1 hour. When I look at this crystal or lattice of this crystal, it is looking at the same. Okay, so then I am going to I have performed some operation on this crystal at time t is equal 0, but that operation gave me the same kind of atomic arrangement that I have at t is equal 0. Okay, so the symmetry operation is one that takes the crystal into a configuration identical to the initial configuration. So the configuration which I have at t prime is same as the configuration which I have at t is equal 0. So the operation which I performed on this configuration at t is equal 0, that operation gave me the same kind of configuration which I have at t is equal 0. That is the reason why this operation is called as symmetric operation. Symmetry operation that we can perform on crystals. Okay, so we will look at different types of symmetry operations in crystals. So the crystal is said to possess a symmetry element corresponding to an operation if after performing the particular operation, the crystal goes into a position indistinguishable from the initial position. So we are going to say that the crystal is going said to possess a symmetry. A crystal is going said to possess a symmetry element corresponding to operation when the after the operation, the configuration which we got, the configuration is same as the initial configuration, right? Then we can say that the crystal is possessing some kind of symmetry. Okay, so there are the most important elements of symmetry are the center of symmetry and axis of symmetry and plane of symmetry. So a center symmetry element can be a center, an axis, or a plane. Okay, you can perform the operation, symmetry operation, at a center, about a center, and about an axis, or about a plane, right? So if you perform the symmetry operation about a center, it is called center of symmetry. If you are getting the same kind of configuration to the initial configuration, when you perform the symmetry operation about a center, then we are going to say that the crystal possesses center of symmetry. We are performing some symmetry operation about an axis, and the recurrent configuration is similar to the indistinguishable from the initial configuration. When we perform the symmetry operation about an axis, then we can say that the crystal is going to possess axis of symmetry. Okay, if the symmetry operation is performed about a plane and the configuration is same as the initial configuration, then we can say that the crystal possesses plane of symmetry. So basically you can have different types of symmetry operations. So here the most important ones are three, that is center of symmetry, axis of symmetry, and plane of symmetry. Each type of symmetry is called a symmetry element. The crystal may have more than one symmetry element, right? All the symmetry elements possessed by a crystal grouped together are called a symmetry group or a point group. Okay, so you can find you can perform different types of symmetry operations, and all the symmetry elements, like about an axis, about a plane, about a center, you can have different types of symmetry elements. All these symmetry elements grouped together is called a symmetry group or a point group, right? So that is what is a point group. Point group is nothing but all the symmetry elements processed by a crystal grouped together is called point group or symmetry group of a crystal. Because of the restriction of the condition of periodicity, the number of possible point groups is not large. It was shown that all possible combinations of symmetry elements lead to 230 space groups divided into 32 symmetry classes. These are grouped into 7 crystal system, right? So because we know that crystal possess this periodicity, that condition of periodicity, because of this constraint or restriction of the periodicity of crystals, there can be only 230 space groups, and these 230 space groups are divided into 32 symmetry classes, and these 32 symmetry classes are grouped into 7 crystal systems. And previous showed that there are only 14 different types of lattices, and you can group these 14 types of lattices into 7 crystal system. Similarly, you can perform some different symmetry operations, and you can find there are only 230 possible space groups, and that are divided into 32 symmetry classes. And these 32 symmetry classes are grouped into 7 crystal system, which we have discussed in the earlier presentations, right? So we have discussed about 7 crystal system in the earlier presentation. So the first one is cubic crystal, tetragonal, orthorhombic, trigonal, rhombohedral, right? So there are 7 different types of crystal system that we have discussed in the earlier presentations. But today we are going to discuss about the structure and packing fraction of different cubic lattices, starting with simple cubic unit cell or simple cubic lattice. Okay. A unit cell, we know what is a unit cell. Unit cell is characterized by a set of parameters. A unit cell is the smallest geometric unit by repeating which you are going to generate the complete lattice. Okay, so unit cell is the smallest geometrical unit. Smallest geometrical unit, the repetition of which will generate the complete lattice or a crystal. Okay, so these unit cell is characterized by the different set of parameters. These are the volume, effective number of atoms, coordination number, atomic packing fraction, and density. So these are the 5 different set of parameters that characterize the unit cell, which is the smallest geometric unit. Which repeating that smallest geometrical unit cell, you can generate the whole lattice of a crystal. Okay, so for each of these simple cubic lattice and base center, body centered, and face centered, 3 different types of lattices of a cubic lattice system, we are going to discuss about these lattice set of parameters. So there are 3 varieties of simple cubic lattice. There are 3 varieties of cubic lattice: simple cubic, body centered cubic, and face centered cubic. So we are going to look at these 5 parameters for each of these cubic system. Okay. So a unit cell is said to be a primitive when the cell has lattice points only at its center, corners, right? We have said that primitive unit cell is the one which has only one lattice point per unit cell, or a unit cell is said to be primitive when the cell has lattice point only at its corners. Okay, only at the corners, if the unit cell has lattice points, then we can say that it is a primitive unit cell. That means that it is going to have one lattice point per unit cell, right? So the primitive cubic unit cell is also called a simple cubic unit cell, and here it is shown. The simple cubic unit cell is shown here. The simple cubic unit cell has only lattice point at 8 corners. Okay, so the volume of the simple cubic unit cell, in case of cubic cell, all the edges of the cube are of equal length. We know that for a cube, the condition is that A is equal to B is equal to C for a cubic crystal, and alpha is equal to beta is equal to gamma is equal to 90 degrees. All the crystal axes are perpendicular to each other, and all the axial lengths. So if you take A along x-axis, B along y-axis, and C along z-axis, all these axial lengths are equal for a cubic system, right? And all the axes are perpendicular to each other. So therefore, the volume is given by this. So volume of the cube is A cube, because A is equal to B is equal to C, so the volume is A cube. So for a simple cubic unit cell, the volume is given by A cube, right? Why the volume is A cube? Because A is equal to B is equal to C for a cubic unit cell, right? So that is volume of a simple cubic unit cell, which is A cube. Next, effective number of atoms per unit cell. So based on this, we are going to say whether it is primitive unit cell or non-primitive unit cell. So a unit cell is a part of an infinite scheme and is not an isolated entity. We know that unit cell is the smallest geometrical unit by repetition of which you can generate the whole lattice, right? So unit cell is not an isolated entity. It is an part of infinite scheme. Okay. Therefore, several adjacent cells share each lattice point. Because of that, this each lattice point is shared by different adjacent shells. As a result, the basis attached to a lattice site contributes only a fraction of its mass and volume to one unit cell. We know what is a basis. Basis is an atom or a group of atoms that is attached to each lattice point is called a basis. And we have generated crystal as lattice plus basis, right? So crystal is equal to lattice plus basis. By generating lattice using repeated translation does not give you any crystal. After generating the space lattice using repeated translations, you have to attach a basis to each of these lattice point. Only then you can generate the crystal, right? So because unit cell is not a isolated entity, unit cell is a part of infinite scheme. So each of the lattice point is shared by its neighboring unit cells, right? So as a result, this lattice site contributes only a fraction of its mass to one unit cell. So let's only one atom having a radius r be attached to one lattice point. So we are saying that okay, each lattice site is attached by by only one atom. So we are attaching only one atom to each lattice point or lattice site. Okay, the effective number of atoms per unit cell for this simple cubic unit cell is that Z. I am denoting Z, and which is effective number of atoms per unit cell. Okay, so the effective number of atoms per unit cell for the simple cubic cell Z is equal to ZB plus ZF by 2 plus ZC by 8. So what is this ZB and what is ZF and ZC? ZB is number of body centered atoms. Okay, so how many number of body centered atoms a particular unit cell have? So that is given by ZB. ZB is number of body centered atoms, ZF is number of face centered atoms, and ZC is number of corner atoms. Okay, so the total number of atoms per unit cell is given by Z. Our effective number of atoms per unit cell is given by Z, and the equation is ZB plus ZF by 2 plus ZC by 8. Okay, so now for this simple cubic unit cell, we are going to calculate this effective number of atoms per unit cell. Okay, so in the 3D array, each corner atom is linked to 8 surrounding cells. So if you look at this simple cubic unit cell, each of the lattice point or each of the atom is surrounded by 8 surrounding cells. So there are 8 surrounding cells. So basically each atom is shared by 8 of them, right? Hence the atom contribute 1/8 of its content to a unit cell. Okay, each unit cell has 8 of its neighbors. So the contribution is 1/8 to each unit cell as shown in the figure, right? So simple cubic unit cell being a primitive cell does not contain lattice point within the body, volume or in the center of faces. So therefore the total contribution comes from the corner atoms of the unit cell and is given by, so ZB, there are no body centered atoms, there are no face centered atoms. Simple cubic unit cell has only atoms at the corners, right? Only atoms at the corners. So there are 8 atoms at the 8 corners, so 8 by 8. So basically we are getting 1. So number of atoms are effective number of atoms per unit cell in simple cubic unit cell is 1. So that is why we call this simple cubic unit cell as primitive unit cell. Okay, so yeah. So we have looked at the volume of simple cubic unit cell, which is A cube, and effective number of atoms per unit cell, which is 1. So the next parameter we are going to look at is coordination number, right? So what is a coordination number? Coordination number of an atom in a crystal is the number of nearest neighbor atoms. So coordination number is nothing but the number of nearest neighbor atoms. Okay, so number of nearest neighbor atoms gives us the coordination number of a unit cell. Okay, so it signifies, the coordination number signifies the tightness of packing of atoms in the crystal. Okay, so how tightly the atoms are packed in a crystal. So this is given by the coordination number. Okay. Around an atom in a simple cubic unit cell, there would be 6 equally spaced nearest neighbor atoms, each at a distance a from that atom. So as shown in figure, if I take this atom, so there is one atom along this axis, there are 2 atoms, 1 and 2, and along this axis you have 2 more atoms, 3 and 4, and along this axis you have 2 more atoms, which is 5 and 6. So basically there are 6 neighbors to any, if you take any number, any atom, you will find there are 6 number of neighboring atoms to each atom. Okay, and the distance between them is a. Okay, 4 atoms lie in the plane of the atom, while one is vertically above it and one is vertically below it. So therefore the coordination number for this simple cubic unit cell is 6. Okay, so the coordination number is nothing but the number of nearest neighbor. Here it is clearly, you can see clearly in this figure that any atom, I am taking an atom A here. For atom A, there are 6 nearest neighbors. So that is the reason why the coordination number for simple cubic unit cell is 6. So the next parameter is atomic radius. I am denoting this atomic radius by R. Okay, so the relationship between the apparent size of the atom and the edge of the unit cell can be determined where one atom is attached to a lattice site. Okay, so atomic radius is a relationship between the apparent size of the atom and the edge of the unit cell. Okay, and the specific direction along which atoms are in contact is identified and applying simple geometry. The relation between the atomic size and the unit cell edge can be computed. Okay, so yeah, so in the simple cubic unit cell, the atoms would be in contact along the edges of the cube as shown in figure. Okay, so along the edges of the cube, if A is the edge of the cubic unit cell and R is the radius of the atom, then A is equal to 2R, R is equal to A by 2, right? So there are two atoms. And the distance, if I take this axis for the atom A, then fifth atom is at a distance A and the sixth atom is also at a distance A. Okay, so the radius is given by A by 2 or A is equal to 2R. So, okay, yeah. So the next parameter we are going to look at is atomic packing fraction. So next parameter we are going to look at is atomic packing fraction. The fraction of space occupied by atoms in a unit cell is known as atomic packing fraction. So what is atomic packing fraction? The fraction of space occupied by atoms in a unit cell is known as atomic packing fraction, and it is defined as a ratio of volume of effective number of atoms in a unit cell to the total volume of the unit cell. So atomic packing fraction is defined as the ratio. A ratio between what? A ratio between volume of the effective number of atoms in the unit cell to the total volume of the unit cell. Okay, so atomic packing fraction is a ratio between volume of effective number of atoms in the unit cell to the total volume of the unit cell. So yeah, so atomic packing fraction is given by this number of atoms per unit cell into volume of each atom. So how many number of atoms we have per unit cell and volume of each atom. So this is the effective volume of the effective number of atoms divided by the volume of the total unit cell. Okay, so that is given by atomic packing fraction is Z into V. So Z is nothing but the number of atoms per unit cell, and this nu, so let us say this is nu is volume of or small v or mu. Okay, so this is volume of each atom divided by volume of the unit cell. Okay, so in case of simple cubic unit cell, Z is equal to 1. We know, we have just calculated the number of effective number of atoms per unit cell for a simple cubic unit cell is 1, right? So for this Z is 1, and we know the volume of the simple cubic unit cell is A cube, and we have just seen that A is equal to 2R, right? So A is equal to 2R, so that is 2R cube, which is 8R cube. So atomic packing fraction is given by, okay, so each atom, we need to calculate the volume of each atom. If each atom is in spherical shape, the volume of the sphere is 4 by 3 pi r cube, where r is the radius of the atom. So substitute all this. So if we substitute all this, so atomic packing fraction is equal to Z is 1 into small v, which is the volume of each atom. So volume of the each atom is 4 by 3 pi r cube divided by 8 r cube. Okay, so 4 2s are, okay, and then there is r cube will go. So what you have is, yeah, so 5 by 6. So that is 0.52. So the atomic packing fraction of a simple cubic unit cell is 0.52. So the next parameter we are going to look at for simple cubic unit cell is the percentage of void space. So void space in the unit cell is the vacant space left unutilized in the cell. So we have looked at the atomic packing fraction. So that is the space occupied by the atoms. So the unutilized space or empty space is called as void space. Okay, so the percentage of void space is equal to 1 minus atomic packing fraction into 100. So we are looking at the percentage. So that is why we need to multiply with 100. And the total volume of the unit cell, if we are taking 1, so 1 minus occupied volume of the unit cell will give us unoccupied volume of the unit cell or void space. So 1 minus 0.52. So 0.52 is the atomic packing fraction. So 1 minus 0.52 will give us 0.48. But now we are looking at the percentage. So that is 48% of the percentage of the space in simple cubic unit cell is unoccupied, or it is a free space. The free space in simple cubic unit cell is 48%, and the occupied space is 52%. So total one is 52 plus 48 is 100%. So the last parameter for simple cubic unit cell is the density of simple cubic crystal. So as a unit cell possesses all the structural properties of a bulk crystal, the density of a unit cell must be the same as that of the crystal. Okay, so if you calculate the density of a unit cell, you can, that is equal to the density of the whole crystal, right? So density is defined as mass per volume, and here we are defining mass as Z into W by V. So where V is the volume of the unit cell and Z is the effective number of atoms per unit cell, and W is the mass of each atom. Okay, so Z is number of atoms present and mass of the each atom, so that will give me the total mass of the atoms present divided by the total volume of the unit cell will give me the density, right? So W, which is the mass of the each atom, is defined as M by Na, where M is the molecular weight of the material and Na is the Avogadro number. Okay, so density rho is given by Zm by Na into V. So I am just substituting this W. So Z is the effective number of atoms per unit cell, and W is defined as molecular weight of the atoms divided by Avogadro number, and there is another ZW divided by V. So there is a V. Okay, so Z, which is effective number of atoms per unit cell, multiplied by molecular weight of the material divided by Avogadro number multiplied by volume of the unit cell. Okay, so we know that Z, for a simple cubic unit cell, Z is 1. Z is number of atoms per unit cell is 1. And yeah, and what we have, M, molecular weight is M, and divided by Na into volume of the simple cubic unit cell is A cube. So M by Na into A cube. So this is density of a simple cubic unit cell. Okay, so yeah, so we have discussed about different parameters starting with volume. So we have started with volume of a simple cubic unit cell, which is A cube. Then we have looked at the effective number of atoms per unit cell for a simple cubic unit cell, which is 1. And then we have looked at the coordination number, that is number of nearest neighbor. Then coordination number for a simple cubic unit cell, we found it is 6. And atomic radius is A by 2. And atomic packing fraction is 0.52, or 50% of the space is occupied and 48% of the space is unoccupied or void space. And the density of the simple cubic unit cell is given by M, which is molecular weight of the material, divided by Avogadro number into volume of this simple cubic unit cell. So in the next presentation, I will discuss about these parameters for body-centered cubic unit cell and face-centered cubic unit cell. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.